Hello friends, welcome again. And as you know, we are discussing the NPTEL assignments with you. That means we are taking some of the questions from the NPTEL assignments which are highly relevant from the GATE exam point of view. And today I'm going to discuss one problem from the metal forming section which I have taken from those assignments, right? And since I'm just picking one of those problems, so similar kind of problems you will find which are somehow or they are somewhat related to that, right? So some modification of that, a lot of problems that you are going to find in the NPTEL assignment on the similar lines. So let's focus on this problem. Just have a look over there what it says. If flow stress of a material is given by, so he has given the flow stress, this variation, and he asks you ideal work per unit volume will be. Now basically he is asking you to find the work done in an homogeneous deformation process. That is the ideal work that you do when you plastically deform a material, as simple as that, right? Now for that I have to make you recall, going further with this, I think if I should make you recall one formula. So if you can recall that formula, then I think you will be able to relate it and you will be able to solve it very easily. Otherwise you may find it a little difficult because he has used some terms and all that. Okay, anyway, so let me just tell you, you must have heard about the work done in an homogeneous deformation process per unit volume. Work done per unit volume, right? So which is equal to what? It is given by mean value of flow stress and natural log of A1 by A2. What does that mean? First of all, you need to keep in mind, when we talk about work done per unit volume, we are talking about the work done, that means work done per unit volume information is given in the stress strain diagram. That is, the area under the stress strain diagram is represented in work done per unit volume information is there. Because you know, if I have to represent simply the strain energy, right, that concept you already know. Let us say if I say the strain energy is equal to what? Work done. So if I have to simply represent the work done, then I will say simply in the force deflection diagram. I will represent it as a area under the force deflection diagram. Okay, but if same information I have to represent on the stress strain diagram, then how do I represent it? I represent it, all the information on the stress strain diagram, that is the area under the stress strain diagram, is represented by the work done per unit volume, right, or strain energy per unit volume. That is how we represent. So that means area under the stress strain diagram. Let's say if I take any stress strain diagram, so if I want to represent the area under the stress strain diagram, then obviously that will be the per unit volume, that is the work done per unit volume or strain energy per unit volume. That way that information is presented. So that concept you are already having from the strength of material. But anyway, since he is representing over here work done per unit volume, so obviously he is talking about the stress strain diagram. But which stress strain diagram? See the value. This value is the mean value of flow stress. Mean value of flow stress. That is the average value of the flow. Flow mean, in this case we normally talk about the true value of the stress. So basically that is I have written it over here, sigma TR. TR means true stress. So average or mean value of the true stress. And over there this is a natural log of A1 by A2, and if you want to write it more appropriately, then this will become the true strain, A1 by A2, or you can write it as L2 by L1 also. Volume is going to remain constant. So this, if I want to write, I can also write it this way, sigma value of true value of stress, mean value of flow stress, or mean value of this, and epsilon. So this formula in any case you have to remember. Why you need to remember? Because for any plastic deformation process that you analyze in metal forming, whether you take the case of forging, whether you take the case of rolling, or whether you take the case of this wire drawing, or whether you take of extrusion, in all these processes you compare the work done in, because what we want to do in these processes, we want to estimate the amount of force that you need to apply in order to deform the material. That is the objective. You want to find out the amount of force that you need to apply to deform that material. And to find that force, to estimate that force, what you do is, you first calculate the external work done in these processes. First you will find out the external work done in that process, and then you will equate it to the work done in an homogeneous deformation process. That means W that you will calculate from here will be equal to the external work done over here. So from there I will be able to get this value of the force required to deform that material. So that means in any case you cannot skip this formula, that has to be. Now point is how it is related to in this context. For me important is that from where does this formula originated? From where did I calculate this value, or this I came to this formula? So if this formula, if you see the origin, if you go back to your basics, then since I am saying that this whole information is represented in the stress strain diagram, since here true stress is coming, then obviously I will be talking about the true stress, true strain. And let us say if I take any material, or let's say mild steel or something that way, so I am going to have a something diagram that way, true stress, true strain diagram for that particular material. Now to find out the work done for this per unit volume, what we do is we take the area under the diagram. We take a small strip over here in this case, and then we say that, let us say I am straining it from an initial strain value of that material, initial strain value of epsilon 1 to the final strain value of epsilon 2. Got my point? What I am doing is, let's say I am taking this bar and I am, let's say, plastically deforming it. Then obviously, let's say if initially I have already strained it by an amount epsilon 1. Now what I am doing is I am deforming it again from epsilon 1 to the next value of the strain, let us say epsilon 2. So when I am straining this, then I want to find out how much work I did in straining this material from this point to this point. Now if you see, so you will say, if you want to find out the work done, obviously the area under the diagram is going to be the work done per unit volume information. As I explained you, already explained you. So this area under the whole of this area under this diagram is going to be the work done per unit information, per unit volume. So if I want to write this one, then I will erase it. Let me just write it. So how did you get this value? You will say work done per unit volume will be what? Now see, when you started deforming from here to here, the true value of the stress was varying from here to here. It means value of stress was varying. Which value? True. We are talking about the true stress and true strain concepts in metal deformation processes. So stress value was varying. So it means it has to be area under the diagram. How I am going to find out? I am going to say simply, if this is variable, and obviously instead of this is a static value. Keep it in mind. Mean value means constant value. So how I got it constant value, I will explain it. But first what you need to do is, first let's say this is the variable over here. It is varying from here to here, and if I simply write d epsilon, that is the true strain, that is the epsilon. If I write this way and it integrate it from here to here, from here epsilon 1 to epsilon 2, epsilon 1 to epsilon 2. So this is going to give me the area under this particular diagram. So this total area from epsilon 1 to epsilon 2, I will be able to integrate by getting it, I can get it by simply integrating this value. So this is variable, and obviously this I have already written as a variable d epsilon. So now if you see, if I want to get a simple formula for work done per unit volume information, so what you do over here, what you did at that time was, we assumed that this value of stress is not varying, which actually is varying from here to here. So we normally take it as a mean value of the flow stress. Why? So that our calculation becomes simple, our formula becomes simple, and we can apply it to the actual situation. Otherwise it will become complicated for us to use that formula or that equation. So that is why what we do is, we take some mean value of the stress, which we called it as a average value of the true stress, which I know even though it is varying from here to here. It was less, more, something that way. So this value of I took this value this way. So instead of taking this as variable, what we did is we modified it for simplification and we took the average value of this stress. Now when we are taking it as an average value, so what you're going to do is it becomes constant. So if it becomes constant, I can take it out and then integrate this epsilon 1 to epsilon 2 d epsilon. Now you know how I can write the epsilon. This is the true value of the strain. So you can write it this way, that is dl, change in length to the instantaneous length, and since I'm writing it in this form, so I need to change the limits also. I'm writing it as L1 to L2. Now it becomes simple, pretty simple, sigma true value of stress into natural log of L, that means it becomes L2 by L1. Or I can write in terms of area, because you know A1 L1 initial area initial length must be equal to final area final length. So if I write it in terms of this, so I can say A1 by A2. Matching. So that means this value of volume, work done per unit volume in an ideal process or in an homogeneous deformation process, I can write this way, and from where I got it from here. That means when I am deforming a material from a certain strain value to the next strain value, and I assumed this one over there as a constant value, therefore I am having mean value. Now why this is relevant in this context? So I don't need to go for this. So if I know this, then I can go backward, reverse, and then I can write it this way. So that much is required for me. Now if that is done, then how I can use this over here? It is pretty simple now. What he has given me, if flow stress of the material is given by this, it means he has already given flow stress, in this case true value of the stress, he has given me this value. That means it is a variable. So what he has given me, I can write it in my own terminology. I am writing it. So he has denoted this bar, so I am writing this, basically he is giving me the true value of the stress, which he denoted sigma, which is equal to what? Alpha, true value of the strain, and which he denoted epsilon bar. So I am writing it with the epsilon square plus c. This is what he has given me. Or you can say it is the same thing which he has denoted over there. He has denoted it by what? Sigma bar equal to alpha epsilon bar square plus c. But I am writing it this way, and since I am having these notations, so I will write it this way. So this is what he has given me. So it means in this formula, and he is asking me to calculate the same thing. He is asking me to calculate work done per unit volume. Ideal work per unit volume, work done in an homogeneous deformation process. He is asking me to calculate this one. That's all. So you need to simply input this value. So what I am doing is, I am simply inputting this value over here. That is work done per unit volume is equal to, just write this value, epsilon of alpha epsilon raised power 2 plus c into d epsilon, and then from any strain value, initial strain value to the final strain value. Now integrate it simply. So what you are going to get is alpha epsilon raised power 3 divided by what? 3 plus c epsilon bar. Sorry, I am writing the epsilon, so I am writing c epsilon, and then units, this changing from epsilon 1 to epsilon 2. That's all. Now see, epsilon 1 he has not given me. He has not given me whether how much he has deformed initially, how much strain he has produced initially. So if he has not given the initial information of how much you have strained it, so I am going to input it as 0. So it means for me this value is 0. So if that be the case, then you just integrate. What you are going to get is alpha epsilon 2 this divided by 3 plus c epsilon 2. That's all. Or if you want to write in his term, in the notation that he has used, so he has used for epsilon, he has used epsilon bar. So can I write, or you can write it same way, alpha epsilon bar divided by 3 plus c epsilon bar. So now see, which option do you have? This becomes this one. This becomes the option A. So option A is going to be the correct answer, right? Now if you see, if you know this one, if you have the idea of this one, then it is very simple, straightforward result. But if you don't have the basic background of this, which most of you try to skip, normally when you try to estimate the amount of load required to deform the material in the different deformation processes, for example forging or maybe rolling and all that, you skip this formula, basic formula. And since you skip this basic formula, obviously you will never think about this the origin, from where it originated. When you don't know about the from where it originated, such kind of problems cannot be solved. So in NPTEL, such questions, many of on similar lines, he has framed many of such questions where he has focused on the basic part of your understanding, not simply direct final formula, input the value and get the result. Okay, so that way these NPTEL assignment questions are going to be quite helpful for you. Okay, so that is all for today. Next time I will come out with some more questions, like today I have taken from production. Next time also I may take some one more question from other part of the production, or maybe from machine design or those areas, so that you have the holistic idea of the kind of questions which are there on the NPTEL assignments. Okay, so that is all for today. See you in the next session. Till then, bye. Thank you.